Bom dia. Eu quero agradecer a presença de todos e agradecer a presença do professor Andrew, em nome não só do Departamento de Geografia e do Programa de Pós-Graduação em Geografia Física, mas também em nome do professor César Hades, que é o diretor do IEA, que infelizmente não pôde estar aqui para abrir essa sessão por compromissos que ele assumiu anteriormente. Mas ele também agradece a presença de todos, em especial ao professor Andrew Gaudi. Também gostaria de fazer uma breve apresentação. Eu sei que a maioria de vocês já conhece o professor Gaudi, mas dizer que ele vem da Universidade de Oxford, né, e que ele é um dos mais renomados geógrafos físicos da atualidade, inclusive tendo sido agraciado com os diversos prêmios, como, por exemplo, a Medalha Real da Royal Geographical Society e também um prêmio da Royal Belgian Academy, entre outros. Ele é o atual presidente da Associação Internacional de Geomorfologia e também foi o diretor, né, desse grupo que é tão importante para nós geomorfólogos, que é o British Geomorphological Research Group, que vocês também devem conhecer bastante. Ele tornou-se diretor do St. Cross College em outubro de 2003 e continua apresentando conferências, dando aulas e conferências também no centro da Universidade de Oxford para estudos sobre o meio ambiente. Os principais assuntos que ele vem desenvolvendo e que ele tem especialidade são assuntos relacionados aos meios desérticos, também geomorfologia especificamente dos meios desérticos, a avaliação do impacto humano no ambiente e também geomorfologia e os efeitos das mudanças climáticas em sistemas geomorfológicos, assim como a geomorfologia aplicada, tratando de diversos assuntos, como vocês vão ver, como, por exemplo, as intervenções humanas, questões sobre conservação, questões de zoneamento e de planejamento ambiental. Então, em nome de todos, eu agradeço a presença do professor Gaudi e peço para que ele inicie a sua conferência de hoje.
Bom dia. I'm sorry I don't speak Portuguese, but it's very nice to see you all here. Thank you for coming, and I am particularly grateful to Dr. Clady for inviting me to come to USP, and above all, for looking after me so well. Thank you very much for that. Today I'm going to be talking in two parts. It's rather like Beijing, with me doing the marathon, but I will be talking for about an hour on the general nature of applied geomorphology, and then I will discuss in the second part of my lecture the role of geomorphologists in the study of environmental change in the future. So for the first part of my talk, I'm really asking two very simple questions. Is geomorphology useful? And are geomorphologists useful? And the answer to these two questions must be yes. And before I came to São Paulo, I was at the Federal University of Minas Gerais, at Sinageo, and there were many papers on applied geomorphology. And I list just a small selection of them here to give you some idea of the sorts of very useful topics that many Brazilian geomorphologists are already working on. Now, one reason why geomorphologists are useful is because many of them are physical geographers, and physical geographers have many skills which in combination give them an expertise which other disciplines do not have. So, for example, we understand the idea of the system. We understand that everything in nature is connected and that you cannot just change one thing in nature. All our actions have a series of knock-on effects. This is a long tradition in geography. The French call it connectivité, the Germans call it Zusammenhang, and Professor Cristoforetti in this country has written on the subject. Another big skill we have is to use our eyes, because geographers work on landscape and they can recognize landforms. If you go to the average engineer and say, here is a Yardang, which is a desert feature, or a Barkan, which is a desert feature, or a Pingo, which is a periglacial feature, they will not understand anything of what you are saying. But we have eyes and we can recognize karstic phenomena, mass movement phenomena, and so on. Another skill of the geographer is to understand the importance of distributions and how the distribution of one phenomenon correlates with the distribution of another phenomenon. And very often you can map landforms, because you can see landforms easily on air photos and on the ground, and use that as the basis for mapping other phenomena related to the landforms, such as soils. We also have technical ability. Geographers still work with maps, with remote sensing, with GIS, with monitoring. Modern geographers know a bit more now about process in the environment. But there are two other things that are very important in terms of our skill. One is that we understand that the world is always changing. There is a multitude of different scales of temporal change. It may be El Niño, it may be Heinrich events, it may be glacials and interglacials, but we understand that the present is not necessarily normal or inevitable. And our final skill, I think, which is very obvious but very important, is that we recognize that different places are different. Oxford is not the same as Sao Paulo. A desert is not the same as a rainforest. A limestone region is not the same as a granite region. We understand, therefore, that appropriate solutions to environmental problems are not universal. They depend upon local circumstances. Now, I would not like you to think that applied geomorphology is the only type of geomorphology. Nor would I like you to think that I do not believe in the inherent basic importance of fundamental research in geomorphology. Even if geomorphology was not useful in any economic or social sense, it would still be a very valuable part of knowledge. But to make ourselves useful is good for society. It's good for bringing money into the discipline, and it's good, this is most important of all, for providing jobs for our graduate students. And in fact, many of the greatest geomorphologists in the history of our subject have been applied geomorphologists. For example, in the 1870s in the American West, geomorphology in its modern form essentially developed. And it was because of the work of great American geomorphologists belonging to the United States Geological Survey, part of the Department of the Interior, who were going to try and understand the West, an area no one knew, and to try and find out where the railroads could be located, where the water supplies were, and so on. And crucial here was the work of people like John Wesley Powell, the great explorer of the Grand Canyon, and G.K. Gilbert. And Gilbert, for example, was an applied geomorphologist, and he did fundamental work on the effect of gold mining on the rivers and the coastline of California. But he also developed our concepts, basic concepts in geomorphology of dynamic equilibrium. And then in the 1930s in America, there was the Dust Bowl. There was the Tennessee Valley Authority, the TVA, which was introduced in order to control erosion by wind in the first case and by water in the second case. And one of the people who worked in this fundamental area was R.E. Horton. And it was R.E. Horton who developed modern quantitative geomorphology and influenced people like Stanley Shum and Richard Chorley and Arthur N. Strehler. And then in the 1950s, there was a great development in the tropics, in areas like Australia and Africa, and so many geomorphologists were employed by CSIRO in Australia or by the British government, for example, in Africa. And then in the 1970s, when I was still a young man, there was the construction boom in the Middle East. And many British geomorphologists went out to the Middle East to be involved with the construction industry. And also in the 1970s, in many countries, we had the introduction of environmental impact statements. So that if you were building some industrial plant, for example, to enable that to happen, you had to produce an environmental impact statement. And then in the 1990s, we've had the development, particularly, of a concern with global change, and geomorphologists have much to say, as we will see in the second part of this morning. They have much to say about the impact of global change on the environment. And finally, in terms of my little potted history of applied geomorphology, we're living in an era now of a minerals boom, all sorts of minerals, including oil. New areas are being developed, both on land and under the sea. And many geomorphologists in Britain are now concerned with submarine geomorphology of, for example, the Congo fan or the Nile Delta or offshore from Norway, because new oil rigs are being built on karst, they are being built on landslides, they just happen to be underwater. And also, as more and more oil is being transported from new oil fields in Kazakhstan, for example, through Georgia to the Mediterranean or to the Black Sea, huge new pipelines are being constructed, and these have to follow a sensible route. And there again, the geomorphologist is extremely important. So there is G.K. Gilbert, a great pure geomorphologist, but also a great applied geomorphologist. And here are two great figures in soil erosion research. H.H. Bennett of the US Soil Conservation Service and W.S. Chappell from the Wind Erosion Unit in Kansas. They were applied geomorphologists, but they did fundamental work on the processes of water and wind erosion and on the rates of water and wind erosion. Now, I believe that using our skills, we have about 9 main roles as applied geomorphologists. And if you think there are more than that, perhaps you'll let me know in the discussion, though the only danger of that is that my lectures will get even longer in the future. Our first role is to use our skill with maps and with our eyes to map resources, gravel, sand, but also to map the location of hazardous situations, and also to describe the physical habitat, which is the basis for much biological life. Our second role, which develops from that, is to use our knowledge of the correlation of distributions, which I mentioned earlier, to use landforms to map other elements of the environment, such as soils. Our third role relates to hazards in particular, and the need to understand the rates at which geomorphological change and hazards are operating. We also, and this is our fourth role, need to know the causes of changes and of hazards. Our fifth role is to predict and model future hazards. Our sixth role is to record what happened in hazardous events so that we can learn lessons from them for the future. Our seventh role is to carry out environmental impact assessments of projects before they occur and to undertake surveys of the success or non-success of various construction programs after they have occurred. And then we move more and more into the human domain. We must not be frightened. Even though we think we are relatively pure scientists, we need to get involved with management, with policy, with planning, and finally in public education and in geoconservation. So that very quickly is the basis of what I'm going to be saying from now on. So mapping is very important, and we do this by using our eyes, walking the ground, using maps, using air photos to produce geomorphological maps. And by developing geomorphological maps, as I've already said, we can develop soil maps through the catena concept or the topo sequence concept. Here, for example, is a picture from Sweden, and it shows some gravel. It's a resource. But this gravel is also a landform. It is an esker produced beneath a glacier in the Ice Age. And if you map eskers, you are mapping gravel resources of a particular type. And that is useful information for the engineer. And here is a colleague, Professor David Jones, from the London School of Economics, working in the Hunza Valley in northern Pakistan, with his air photos, with his base maps, establishing the extent and history of glacial movements in the 20th century, which I shall mention later. So that's about mapping. Let us now think about hazards. And one feature of hazards research is that everyone, when you say the word hazard, thinks of dreadful meteorological and geophysical events. Events like the Boxing Day tsunami in Southeast Asia in 2004, or the great Pakistan earthquake of 2005, which caused so much loss of life, not least because of the huge mass movements and debris flows that it created. Now, I have no doubt that those are very significant and important events, and that the geomorphologist has much to contribute to understanding their impact. But the point I want to make is that there are many, many geomorphological hazards of a less dramatic type, but which are nonetheless very important if one is to successfully develop particular areas. So, for example, if we take deserts, dunes move. Wind erodes the ground surface. Because of the lack of vegetation, if there is a big storm, you get the development of deep gullies, and you get the entrenchment of alluvial fans. You get flash floods coming down desert rivers. You get the weathering of building foundations by salt attack. You get certain parts of the desert surface producing very dense storms of dust. You get the removal of groundwater and hydrocarbons to produce severe ground subsidence. And the addition of water to porous soils may cause them to collapse by a process called hydrocompaction. Now, there are many examples of engineers in the Middle East in the 1970s using the techniques and the knowledge they had developed in England or in Korea in a country like the United Arab Emirates. And I can tell you that it was a disaster because they did not have this knowledge of these specific place or region-related hazards. There is a dust storm. There is a dune. Different types of dune move at different rates and can attack engineering structures. So we need to have a long-term record of the movement of different types of dune. And this is a slide which is terrible, and I'm not at all proud of it. It's good for educational purposes. It shows one particular type of desert surface in Egypt, a surface which is called the stone pavement, which is a surface armor or lag of gravel that overlies underlying fine-grained material. And what you can see here very clearly is that this is a very vulnerable surface in one sense, and that if you drive on it, you expose the fine material beneath the armored lag to wind attack. And then the surface will not recover for decades. Not only that, but because you have disrupted the surface armor, that fine material gets blown up into the air by wind action. And wind, transported material in the air, is bad for your lungs, it's bad for your eyes, it's bad for airports, it's bad for driving on roads. And one group of British geomorphologists worked in Saudi Arabia to identify the dangerous surfaces that produce dust. And they mapped those and said to the government of Saudi Arabia, you must not allow people to drive on that particular type of surface. Otherwise, you will have a big wind dust problem downwind in your city. And here is a dramatic illustration of the hazard produced by subsidence because of the withdrawal of groundwater. This is a slide taken from the Central Valley in California in the USA, and you can see there that the land has subsided by about 9 meters since the 1920s. That's a fantastic amount of subsidence and has many engineering implications. One can say something very similar for periglacial areas, another part of the world where development is going on very quickly, another part of the world where most traditional geomorphologists and engineers do not have a great deal of knowledge of the particular environmental problems there are. So we get the problems of decaying permafrost, which we call thermokarst. Subsidence occurs, the land goes all wet and horrible. And then you get the growth of ice masses within the soil, things like pingos and pulsars, frost mounds, which create problems for foundations. You get enormous floods by the melting of snow and ice in the spring and early summer. You get huge surges in some periglacial areas of glaciers. Glaciers can be very unstable. And then in periglacial areas, particularly the area of thaw above the permafrost, generates a lot of debris flows, and also the exposure of riverbanks and coastlines to the atmosphere as erosion takes place causes the permafrost to melt, so it removes the glue that holds the riverbanks and the cliffs together, and so you can get very massive rates of erosion in periglacial areas, massive erosion of river and coastlines. And then, of course, you also have the effects of avalanches. And avalanches do not just occur anywhere. They occur in specific tracks that come down the sides of mountains. There's a geomorphological indication of where avalanches take place. And you do not, if you are sensible, build beneath an avalanche track. So we have subsidence of permafrost, we have surging glaciers, which we can identify because they have very characteristic twisted, deformed moraine. It's very dangerous to build near the bases of such glaciers. And then, of course, we have coastal environments, and again, there's a huge array of geomorphological hazards. We have areas where sea level is rising very fast or sinking. We have the whole question of dune movement and decay in coastal areas. We have many very weak and feeble landforms like barrier islands. We have some coastlines that retreat at some meters a year, and I mentioned periglacial coastlines earlier. Some of the periglacial coastlines in Alaska, where the permafrost is melting, are eroding at rates up to 40 meters a year. 40 meters a year. And then we have hurricane attack. We have accelerated siltation associated with the development of salt marshes. And, of course, we have the horrors of tsunamis. But in spite of these hazards, people build in the wrong places. So we need information about the rates at which coastlines retreat. And now I want to talk very briefly about one particular environment, the Hunza Valley in northern Pakistan, on the border with China. I went there in about 1980 to have a look at a great new road, the Karakoram Highway, that had been built by the Pakistanis and the Chinese, linking their two countries and going across a col in the mountains at over 5,000 meters above sea level. And a lot of geomorphologists, particularly Chinese geomorphologists, were involved in the construction of this extraordinary road. But just look at the range of geomorphological hazards they had to contend with. Glaciers that surge. Some do not, some do. But the ones that surge can move many kilometers in a matter of just a year or two or three. And they come very close to the route of the road. And then in the valley bottoms in the Karakorams, it's quite dry. There's not a lot of vegetation. So you get a lot of erosion, a lot of denudation. And then you have glacial outwash and rivers that carry huge loads of sediment. So you get many siltation problems. You get many problems from the accumulation of debris. And then you get glaciers moving forward and damming rivers, which generates big lakes, which then fail, and you get enormous walls of water, enormous floods coming down streams within the area. And the same process is produced by great landslide or mudflow dams across rivers. Again, lakes develop, the lakes fail, and then you get great floods. And then you get meltwater channels coming from the glaciers. One year they come out of one mouth, another year they come out of another mouth. They're always shifting. This is a nightmare for road construction. And then, although this isn't very important, because it's dry in the valley bottoms, there's a lot of weathering of concrete produced by salt. And then you get a huge array of mass movements in the area. It's very steep, not much vegetation. It shakes occasionally due to seismic activity. And so we get mudflows, we get rockfalls, we get landslides. And finally, because of the fact it's a dry area, with much wind generated by mountain winds, we have dust storms which create problems for the road as well. So this is what the Hunza Valley looks like. It's one of the steepest places on Earth, along with Nepal. Very steep relief, very dry, very dangerous. And there is the road running along beside the river, hugging the hillside. And these are the sorts of problems a trained geomorphologist with eyes can recognize. In the foreground of this slide, there is a great landslide dam. And behind it, there is the river. And behind the river Hunza, there's a layer of fine material, flat-bedded, with a flat top, which is lake sediment. So the landslide dammed the river, produced the lake, which produced the sediment. This is an indication that downstream you have to locate your road and your bridges with great care. You have to over-engineer because of these extreme events. And they did fantastic work, the Pakistani and Chinese geomorphologists and engineers. But they did make some mistakes. For example, in this dry environment, there are many great alluvial fans that come down from the mountains towards the valley. And alluvial fans are generated not just by stream flow, but by debris flow. And debris flows carry big boulders, and they shift rapidly. So you see that in this picture, the engineer built a small culvert to carry a normal stream. But if you look behind, you see this was rather silly and stupid, because there are huge great boulders meters across, which of course could not possibly go down such a culvert. So this also links in with another type of applied geomorphology I mentioned, which is post-construction surveys. We went along the road recording all the things that the geomorphologists had got right and all the things that the geomorphologists had got wrong. And so we will learn in the future not to build culverts of that type in that particular geomorphological environment. But it was one of the most horrible, dangerous places I've ever worked. On the far side of the valley you can see the road. I was on that the previous day, and you can see the huge rockfall that is taking place into the Hunza Valley beneath. It's a very, very difficult environment in which to build a road. So I've been trying to explain that there is a huge diversity of geomorphological hazards. Not these grand geophysical processes, but rather more ordinary, mundane processes which are very important for us to understand if we are to develop these particularly challenging environments. And as I say, it's very important for us to determine the rates of change of geomorphological processes, of landforms, and of hazards. And you can read this slide as well as I can, so I won't go through it in great detail, but there are many ways of determining rates of change using air photographs of various ages, remote sensing images of various ages, and they now date back, satellite images, for 40 years, maps of different ages, ground photographs, including tourist postcards, archives. And then we can monitor change using GPS, for example. And then we can use cores from lakes or bogs or swamps to estimate rates of, for example, erosion and siltation in the past. So here's some air photographs just showing the change of a bit of the coastline of southeast England. And we have a record here of how the mudslides have developed throughout the 20th century and into the 21st century. Another important role, you'll remember, is post-event assessment. When a great big hazardous event or a disaster occurs, it's very important to make a record of what actually happened. How big was a flood? What damage was done to engineering structures? What other geomorphological change was achieved? What were the discharges that were involved? Which areas were sensitive, which ones were not? Were there special processes operating? For example, I went to Swaziland in southern Africa after a great flood in 1984 and found that the most important process in the flood causing damage was the fig tree, Ficus sycamorus, which grows along the river channels. And that tree, when it was knocked down by the flood generated by the cyclone, battered the bridges, broke them down, and so on. Now there's a lesson there that if you're designing a bridge, you need to be aware that manic, dangerous fig trees need to be allowed for in the design of the bridge. So you have a flood event. And this is a slide from northwestern Australia, from the tropics, in a place called Geeky Gorge. And the slide is taken in the dry season, and the river level is low. But you can see from the bleaching of the limestone that in the summer months, the flow is very much greater. But in some years, when there are tropical cyclones, the flood levels are probably even higher. But there is no gauging record on this river. So if the engineer wants to build a bridge, how does the engineer design it to accommodate the sorts of discharges one must expect 100 years from now? Well, the answer is that rivers like this in flood deposit rubbish. They deposit trees, they deposit sediment. And that enables you to reconstruct the height of a flood event. You then need to be able to date that flood event, and you can date the rubbish with radiocarbon or with optical dating. And you may find there have been a series of floods over a period of 1,000 years at certain heights. That's useful. But it would be even better if you could estimate the discharges that were involved, not just the heights. So you need to measure the cross-section of the flood, the slope of the flood, and the roughness of the channel. And then using Manning's formula, you can create the discharges that came down this river using slack water deposits over a period of 2,000 years. That is very useful information for the engineer who has to construct a bridge in an area where there is no gauging information. I mentioned post-construction assessment, and I mentioned the Karakoram Highway where that was undertaken. But of course, many engineering schemes have adverse environmental effects. You remember earlier I said you cannot change one thing in nature. So engineers like hard engineering solutions. But do they always consider the impacts that those hard engineering solutions have? One has, for example, to consider a coastline as a system. And if you build erosion control measures like these groins at one point, then obviously it will have an impact on sediment budgets downdrift, which may lead to accelerated erosion downdrift. So one needs to have knowledge about the impact of groins, seawalls, and so on, away from the site where they were constructed. And this little case study from southern England indicates how one quite small engineering intervention can cause very expensive problems. This is on the English Channel, and it is quite an exposed coastline. And in fact, if you draw a line southwestwards, directly from there, you will hit Rio de Janeiro. So the wave fetch is enormous. And because it is an exposed coast, a harbour was constructed called the Cobb, which is a hard engineering structure. On this side here, as a result of the construction of that harbour, you had an interruption of the longshore drift and sediment accumulated. So you have a nice broad beach. On the other hand, when you go to the far side, there is no sediment, or very little, because it has been stopped by the construction of the harbour. And as a result of this, with a very narrow beach, you get a lot of erosion at the base of the town of Lyme Regis. And Lyme Regis is built on clay. It's built on wonderful lias clay from which all the great dinosaurs came. But clay is horrible to build on because it's subject to huge landslides. And you can see behind the beach in Lyme Regis, it's green. There's trees, there's parks. How lovely. Oh no. It's green and it's parks because all the houses that used to be there collapsed. And houses are still collapsing. And so geomorphologists are now involved with trying to rectify the problem. And what they are doing is trying to redesign the shape of the harbour so that it has a more natural equilibrium shape. They're also trying to think of ways of bypassing sediment. They're also thinking of ways of reducing groundwater levels to reduce the amount of landsliding, and so on and so forth. But here is one simple little example of an engineering structure which has had a whole series of implications, and where geomorphologists can give advice about how you can overcome the problems created by the engineering structure. So there is the beach in a storm. The sea wall is being undermined, and they've spent now £15 million, whatever that is, $30 million, trying to solve the problem. It's only a small town. And then we must get involved with people. We must get involved with planners. And it's very important in many countries now that geomorphologists are involved with what Americans call zoning, whereby we produce maps of areas which one should not build in. And one can, for example, think of particular zones where there are problems in earthquake-prone areas. And we map those particular zones and advise that construction does not take place in them. So you do not encourage people to build on artificial fill or on cast in an earthquake-prone area. So we have to map the fills, we have to map the cast. We also need to identify areas that are suffering from neotectonic activity. This is very important if you are going to build a nuclear power station. And again, there are a lot of geomorphological indicators that enable us to build up a map of zones where there is particularly serious likelihood of neotectonic activity. The same with floodplains. I've greatly enjoyed seeing the floodplains of this city and seeing the old photographs and maps of them. But it's very important in many parts of the world that we can recognize where are the active floodplains. How big really are the floodplains in response to a 100-year flood or a 20-year flood? And again, there are many indicators that enable us to produce maps of floodplains showing those parts of them which are hazardous. And now, ladies and gentlemen, as they'd say in America, we're having an advertisement. This is for a little bit of work I've done with my wife, Dr. Heather Viles, on salt weathering hazard and how we got involved with planners on this. Now, salt is a very serious weathering problem. When you get the build-up of salt in the pores of concrete or rock, the crystals expand and bang. Also, some salts take up water from the atmosphere. When the temperature and humidity conditions are right, they hydrate, and again, boom, you get a volume expansion. And also, salts react with iron reinforcements in concrete buildings and cause them to corrode. Now, geomorphologists know this, because for many years we've been doing experiments in the laboratory, as here in Oxford, with an environmental cabinet and an idiot technician. And we can show that certain types of rock, when subjected to certain types of salt, can cause very rapid disintegration to occur. So we know this process operates, but a lot of buildings have been built in sensitive areas where the engineers have not been aware of this process. So we need to try again and produce a zoning map so that town planners do not permit building in salty areas in drylands and various types of city. So we can map damage. We can try and look at the different salts that there are, the depth down to groundwater from which salty solutions can migrate. We can assess the resistance of materials used in construction to salt attack. We can try and find resistant resources by mapping particular types of non-salty gravel. But the key thing at the end of the day is to produce a zoning map. And groundwater height is very important, and the nature and concentration of salts is very important. This is just how important the process is. This is a pipeline that was constructed in Namibia, in southwestern Africa, and 2 years later, the pipeline was finished. It was no good. It was kaput. And the salt in this coastal desert salty environment had reacted with the concrete and with the iron reinforcements. And it's a huge pipeline, about 2 meters in diameter. And here is a nurse's home in Bahrain in the Gulf with one of my colleagues who's now been knighted, Sir Ronald Cook, for scale. He's a small man. But you can see the foundations of that building and the pillars of that building are falling to bits. And this is salt. And it is built on a low-lying area with very high salt concentrations, high groundwater level, and the groundwater migrates by capillarity up into the concrete and causes it to rupture. So we developed a map for the government of Bahrain based on the depth of the water table and the concentrations of salt and the mapping of previous damage of buildings And essentially, in red, we showed them the areas which were particularly dangerous from the construction point of view. And we said, this is where you should not build your factories, your airports, your hotels, and so on. Now, the final little thing before the break I'd like to talk about is the role that we play in geoconservation and in explaining landforms and landforming processes to the general public. We should have a role in education and in conservation. We should have a role, as I say, in explaining beautiful landscapes to people. We have a social responsibility to do that. And we can produce geomorphological trails. We can produce notice boards. We can produce interpretation centres. We can produce websites. And have no doubt that people in society like geomorphology almost as much as we do. I love geomorphology because I love beautiful landscapes. When I drove down the Serra do Mar, I got a great thrill the other afternoon. Unfortunately, we could not stop. There were no belvederes. There should be belvederes with interpretation boards so that people can enjoy that beautiful scenery and understand it. But millions and millions of people go on holiday to see geomorphology. And do we serve them properly? Probably no. Do people in Rio really know about how the sugarloaf formed? Do foreign tourists coming to Rio understand how that fantastic landscape originated? I think we have a very important role in that. And of course, landforms are a very important part of what is now being called geodiversity. They have their own intrinsic value, but they have a cultural value to society. It may have a spiritual value, particularly in countries like China. There's the aesthetic value. There's the economic value because it's valuable for tourism. Landforms have a value in the Earth system, and they have an educational and research value. So protecting, conserving geodiversity should be done for a whole variety of reasons. And Gray goes further and says that actually geodiversity underpins biodiversity in its life support system. And if you have a very diverse river valley with a diverse range of landforms, you have a diverse range of habitats. So the maintenance of biodiversity and the maintenance of geodiversity are related. And in America now, people like Bill Graff are heavily involved in trying to reconstruct the natural river floodplain habitat so that once again it can be the right habitat for various species of birds. So they're historical geomorphologists. They're using old photos, old maps to see what the natural floodplain was like before it was destroyed by humans, and they are trying to get back to that original position. But of course there are many threats to geodiversity all the time, and we need to try and persuade governments, both state, local and federal, that it is wrong to destroy the most important geomorphological features in one's country. One's got to try and make sure that the impacts of all these processes are reduced as far as is possible. And so now there are many international programs at global, regional, local scales to conserve. And I mention here World Heritage Sites and the UNESCO Geosites and Geoparks programs. And I was pleased to see when I was in Minas Gerais that there are plans to make more state parks to protect some of the wonderful karstic landscapes that I was able to see with Augusta Aula. So a lot of work is going on to protect landforms, and geomorphologists need to be involved with these programs. And so the IAG, which Clady said I am president of, has now become involved with reviewing proposals for World Heritage Sites. And these are put up by various individual national governments, and then they are assessed by a panel of global geomorphologists to see whether they really deserve World Heritage designation. And these are the sites for which we suggested reviewers in 2007-8. But there are still huge numbers of wonderful global landforms which have not been given World Heritage designation. And I just show and mention a series of them there. The great Inselbergs and granite weathering features of central Namibia, the Paracutin volcano in Mexico, and so on. Now, that brings me to the end of the first part of my talk, so we can now have a little break, and then I will get on to geomorphology and global change, the second part of my talk. Obrigado. Thank you very much to those of you who've stayed. That is a great compliment to me. You had the opportunity to leave, but here you all are. Thank you. I'm going to talk for this second part of my lecture about global change, particularly future global climate change, and the way in which this has huge implications for geomorphology. And again, I think that as geomorphologists, we should be involved with all the thinking about global change. If one reads the reports of the Intergovernmental Panel on Climate Change, which come out every few years, one finds that many disciplines are heavily involved, particularly biologists and hydrologists and climatologists, but the geomorphological input is not as big as it should be. And yet, in the view of many people, global change in the future, global warming, is the most serious problem facing humankind. This is the view of people from different parts of the political spectrum, even in America, with Arnold Schwarzenegger in California and Al Gore from the Democrats seeing global warming as really a great threat to the American way of life and to the world more generally. And the same is true of British politicians, British scientists, and British economists, and I won't bother you with the names of the other people on this slide. Now, one point I want to make goes back to something I said in the last part of my talk, and that is the importance of particular places, particularly sensitive places in the future. There are 4 global change hotspot types that have implications for geomorphology. There are those areas where the climatic scenarios suggest that the degree of change is going to be particularly great. This is true of high latitudes, as in northern Canada, in permafrost terrain, where temperatures may go up this century by 8 degrees, rather than the 1.5 to 6 degrees which is predicted for the world as a whole. And then there are those places where it is predicted that the amount of rainfall and of soil moisture change will be particularly great, and these include the high plains of the USA, not least in Texas, the home of George W. Bush. What does Fora Bush mean that I see on the buildings? And then there are hotspots which are sensitive because they are fragile. And these are geomorphologically significant places, like, for example, the eastern coastline of the United States of America, where you have heavily populated barrier islands, Cape Canaveral, Cape Hatteras, Cape Cod, the whole shoreline around New York. It's all low and fragile. It's made of sand. Then you have other places which are sensitive because of their position. And here I'm thinking of low-lying deltas in the tropics, which may be very prone in the future to both inundation and to hurricane attack. And then the fourth type of place which will be very sensitive, and again it's geomorphologically important, are places where thresholds may be exceeded. So, for example, in the high plains of America, there are sand dunes which are stable-ish. Under present rainfall, they are covered in a certain amount of vegetation. We're just not quite sure whether they're stable or unstable. Any significant change in soil moisture or vegetation cover will make them very unstable. There are coral reefs in the Caribbean that can tolerate the hot water just, except we know that in warm El Nino years it's just too hot for them and they get bleached. So a couple more degrees of temperature rise in a warmer world and those coral reefs will be very, very badly affected. And then, of course, if you are just on the margins of permafrost in Canada or Alaska or Siberia, and the temperature just goes up a little, the permafrost will start to melt very quickly. So there are various environments which will be very susceptible to global warming, various geomorphological environments. And the amount of warming that the Intergovernmental Panel on Climate Change is proposing, and this will be very familiar to you, is something between about 1.6 and 6 degrees by 2100. That's the global figure. And this process of warming has already started. Of that, there is no doubt. The world as a whole has been warming since about 1970. And one of the roles of the geomorphologist is to try and see how the geomorphological environment has changed since 1970. To try and get some idea of the speed of geomorphological change, to get some idea of which are the sensitive environments over the last 30 years. So change has already started, and we see that, for example, with the distribution of Arctic sea ice in the northern hemisphere. Since 1979, with a warming of about 0.5 degrees or 0.6 degrees, 20% of the polar ice cap has melted away. we see the situation with glacier retreat in the 20th century. And in the tropical mountains of East Africa, in the Andes, in Patagonia, in New Zealand, in the USA, many glaciers have retreated very fast. Not all, but many. Some are advancing because they are being fed with more rainfall, but most glaciers in the world have been retreating, and they've retreated at 20 to 70 meters per year on average in the last 100 years, with a temperature rise of 0.8 over that period. And hurricane activity has changed, according to Professor Kerry Emanuel, since 1970 particularly, and that as sea surface temperatures have gone up, so the development of hurricane intensity in the western North Atlantic has gone up. There seems to be a very good correlation, according to Professor Emanuel. So we already have change. We can already identify some areas being altered very significantly. But as I say, in the future, there may be a whole series of geomorphological environments which will change dramatically. And I just mentioned here ice shelves, valley glaciers, permafrost, dunes, coral reefs, and hurricane-prone coasts. Not only is temperature going to rise in a warmer world, but so, according to the Intergovernmental Panel on Climate Change, will rainfall. And I'm sorry this diagram is not particularly clear, but in brown you can see, for various scenarios, areas where rainfall may decrease by 20% or more. You can, if you wish, concentrate on Brazil. But this is the Intergovernmental Panel's view, and one sees in particular that some of the world's drylands, like the Sahara and southern Africa and the Middle East, which are dry today, will get even drier. There'll be an accentuation of drought. But some of the models, as we'll see in a moment, are really very frightening about Amazonia's future. Amazonia is under stress from various human pressures, but were droughts like that of 2005 to occur, and were there to be forest dieback, then there would be extraordinary geomorphological changes in Amazonia. What sorts of changes, I ask? I do not know the answer, but it is a very important research priority, because many of the climatic models used by the IPCC in 2007 do predict a substantial reduction in rainfall in certain parts of Amazonia. And you'll notice that the bottom prediction from the Hadley Centre in the UK suggests that precipitation averaged across Amazonia could be reduced really rather substantially by the 2040s. So what are the implications of this geomorphologically? Not only will precipitation be reduced, but also, of course, with an increase in temperature, there will be less soil moisture. And in addition, you have the other human impacts, deforestation, fire, changing the nature of the rainforest as well, in terms of albedo, surface roughness, moisture output by transpiration, which could have a positive feedback effect or a combination effect with global warming. The same possibility exists for Africa, where a paper in Science in 2006 by De Witt and Stankiewicz tried to look at how drainage density, the amount of river channel per square kilometre, would change with changes in rainfall. And you'll recall that quite a lot of Africa in the Kalahari is going to get drier. That means that the drainage density will change. They're trying to model this. And drainage density equals water supply for a woman with a bucket on her head. And if, as rainfall goes down and drainage density becomes less, the lady with the bucket on her head will have to walk further. So a major geomorphological change may take place, which is being modelled here in response to changes in rainfall, which will have human implications. Now, globally, in a warmer world, precipitation will increase. Globally, we will get an intensification of the tropical circulation. More heat means we boil the kettle, we have more convection, we have more moisture in the air. But the air that lifts up in the tropics has to come down on the poleward side of the Hadley cell. Subsiding air equals drought. So areas like the Mediterranean basin will get drier. Seasonality of rainfall will change. And I'll come back to that. It's very important in Europe. We will get more moisture in cold regions. Cold regions cannot hold much moisture. As they warm up, there will be more moisture. This has implications. And then in many parts of the world, we'll have changes in rainfall intensity. More energy in the system, more convection, more thunderstorms, more floods. And we've seen that in many parts of the world since the 1970s. Now, in desert regions, the modelling suggests that with a 2-degree centigrade increase in temperature and a reduction in precipitation of 10%, you get a stream flow reduction of 60% or more. So this is what is likely to happen in many of the world's drylands. And that has great implications for water supply, for great cities like Perth in Australia or Cape Town in South Africa. But it has great implications for the nature of river channels and geomorphology. And here is the map for Southern Africa, showing in yellow areas where the precipitation and increase in temperature will mean that runoff goes down by more than 60%. And you'll see some areas where, because of increased monsoonal activity over the Indian Ocean, there'll be an increase in rainfall, as, for example, in Madagascar. More rainfall, less rainfall, has implications for geomorphology. And so we've got this curious thing that in the future in the world, we'll have more droughts and more high-intensity events. In other words, the variability of precipitation and therefore of river flow will change very dramatically. And this is a recent study produced and published this year, which shows just how important droughts may become in certain parts of the world. Now, this was a sort of diagram produced for George W. To try and persuade him that America was going to suffer from global warming. And indeed, there is truth in this, because the American high plains, in addition to being one of the world's major grain-producing areas, is an area, as I said earlier, just at the margins of what is possible in terms of aeolian processes. In good years, there is little dust. In good years, there is little dune movement. But with an increase in temperature, with a decrease in precipitation, this whole area could become destabilized, as it did in the 1930s, when we had the Dust Bowl. We had 100 dust storms in the year in the 1930s in northwest Texas and Oklahoma and Kansas and Colorado. Topsoil being blown off. We had environmental refugees, the Okies of John Steinbeck's novels, being forced to flee from the high plains to California. Black blizzards. This took place in the 1930s. It may become the norm by the 2040s. And not only will the dust storms become more frequent, but also it may be that these semi-stable dunes will start to move. And again, we know this has happened in the past, because geomorphologists, using optical dating of dunes in the high plains, have shown that they have been repeatedly mobilized during drought phases over the last 9,000 years. This is very powerful evidence, I think, to policymakers that here there is a big threat to a very important agricultural part of the US of A. And my colleague in Oxford, David Thomas, has recently published a paper in Nature using the climate models for Central Southern Africa to show that the whole mega Kalahari will become destabilized. It's an ancient desert now covered in vegetation. Huge dunes covered in trees, like you have in many parts of Brazil. Ancient Pleistocene dune fields. Well, the climate models developed by David Thomas and his colleagues suggest that many of those now stable vegetated dunes, stretching all the way from the Orange River through Botswana, into Zambia, into Zimbabwe, into Angola, will become destabilized by 2100, with huge implications for the pastoral industry in particular. And then we have the whole question of what's going to happen in terms of tropical cyclones or hurricanes in a warmer world. Now, plainly, tropical cyclones are geomorphologically very important. In 1984, there was a hurricane in southern Africa where there was 900 millimeters of rainfall in 2 days. Mean annual rainfall of the area is 900 millimeters in 365 days. And infrastructure was destroyed, floodplains were transformed, slopes were destabilized, coastal lagoons were filled with silt, corals died. Now, intuitively one feels that in a warmer world, hurricane distribution, hurricane frequency, and hurricane intensity may change. And many people believe that there is a temperature threshold for cyclone generation of about 27 degrees centigrade. So as the ocean warms, that zone which can generate hurricanes, it is argued, may expand. And the Australians have modelled this for Australia, and in grey you can see the number of hurricanes that cross the coast every decade today, and in yellow you can see the predicted number of cyclones that will cross the coast per decade by about 2100, with a doubling of greenhouse conditions. So today you get, for example, 4 cyclones crossing the coast per decade near Port Hedland in the tropical northwest, the Australian modelers suggest this will treble to 12 cyclones per decade along that coastline. So if seawater temperature thresholds are crossed, it may be that we'll get a bigger geographical spread of cyclones. As water gets warmer, it is possible that the hurricanes may become more intense, and as the water gets warmer, it is possible there will be an increase in frequency. I keep saying it is possible, because there is indeed quite a lot of debate and controversy about the extent to which hurricane generation is controlled by sea surface temperature rather than other atmospheric conditions, particularly in the upper atmosphere. But obviously, if there were more hurricane activity, more intense hurricanes in particular, then we can expect a series of geomorphological changes, slope destabilization, scouring of river channels, more input of sediment into reefs and lagoons, more storm surges to cause coastal erosion, and increased wave attack on atolls and so on. And again, there may be some coastlines which will be particularly sensitive. One of these could be the northeast coast of America, which doesn't get many cyclones today. But if you think of New York and New Jersey, Newark, it's very low-lying, very heavily populated, very fragile. And if one gets a major cyclone on that bit of coastline, it will be horrendous. And it will cause a change in the attitude of the American government towards global warming, you mark my words. Another important effect of global warming is going to be on snow. And snow is hydrologically very important. Snow cover will get less. More precipitation will occur as rain rather than as snow. The time at which snow melts will change. So the hydrology, the regimes of streams in areas with snow will be transformed. And the Rhine is the biggest, or at least the most important river in Europe. And on the one hand, we'll probably get warmer summers and less summer rainfall, but winter rainfall may be up. But also, we're going to get changes in snow storage during the year. Anyway, the overall result of this story is that discharge of the Rhine will go down 30% in the summer months and go up 30% in the winter months by the end of the century. That's a major change in the seasonality of flow. Geomorphological processes are also greatly affected by vegetation cover. And in a warmer world, vegetation belts will shift very substantially. 180 meters for every degree rise in temperature. So on mountains, vegetation belts will in total, if temperatures go up by a few degrees, migrate by some hundreds of meters, and with them the location of different geomorphological processes. This is a slide of New Zealand, the Southern Alps, and it shows the relationship between altitude and vegetation. And there are zones there where you have periglacial processes. There are zones there where you have mudflow generation and alluvial fan formation, and you have a zone in the middle where you've got trees. And there you will have particular geomorphological processes and some stability. All these zones will shift in a warmer world, and with it, geomorphological conditions. This is a fantastic slide of New Zealand. It's the only one in existence with no sheep. Forest belts, vegetation belts, may also change latitudinally very substantially. Particularly the boreal forest covers nearly a quarter of the Earth's land surface, extends all the way from Vancouver to Vladivostok. Models suggest that it will move northwards in the northern hemisphere, so that you'll get migration by, again, some hundreds of kilometers latitudinally. This has all sorts of nature conservation implications and so on, but if you change vegetation at this scale, you will affect geomorphology. And I mentioned that with potential changes in the Amazon rainforest as well. And then, of course, temperature change itself is very important in the cryosphere. And a quarter of the Earth's land surface is underlain by permafrost. It covers huge areas of Siberia, Alaska, northern Canada, and China. And the Canadians have modelled the likely impact of temperature rise on the distribution of permafrost in Canada. And you'll remember that this is an area where temperature rise will be particularly high. And in grey, on this map, is shown the areas in which permafrost will disappear altogether. And in pink, you'll see areas which now have continuous permafrost, where there will be discontinuous permafrost. Now, the change from permafrost to non-permafrost has huge geomorphological and engineering implications. As permafrost melts, you will get thermokarst. As permafrost melts, you'll remove the glue from slopes. As permafrost melts, you will get erosion of shorelines to lakes and the sea, and erosion of riverbanks. The layer that thaws every year will get deeper, generating more debris flows. And there'll be great changes in runoff seasonality and changes in the degree to which groundwater is recharged. So periglacial areas will be transformed. And the growth of thermokarst obviously has enormous engineering implications. But the nature of the thermokarst that develops will depend upon particular soil and geomorphological conditions. Shorelines, as I've already said, will be prone to massive rates of erosion. And here's an example that's going on today. As permafrost degrades in Alaska, the coastline is retreating at 40 meters. And here is a mass movement produced by the melting of permafrost, a huge mass movement feature there developing. And then there are the implications of the melting of the world's great ice sheets. There is the worry that in a warmer world, ice shelves like the Ross Sea ice shelf, which act as a buttress on the main West Antarctic ice sheet, will disappear. And we've seen some very serious loss of ice sheet in the last decade or two, particularly with the loss of the Larsen B ice shelf. So there's always the worry that the Antarctic ice sheets could be destabilized and send vast amounts of water into the world ocean. That is a possibility. But of course the big argument is, how fast is the Antarctic ice going to melt? Is it going to be fast, or is it going to be slow? On the one hand, with higher temperatures, it will melt more. On the other, with higher temperatures, there'll be more precipitation, more nourishment with snow. So in the 1980s, people felt that the Antarctic ice would probably melt quite fast and cause world sea levels to rise by 3 meters by 2100. That is no longer the view. The view now is that the increase in snow accumulation will largely offset the effects of increased ablation, though not in Greenland. And as a result, the Intergovernmental Panel believes sea levels may only rise by 0.5 metre by 2100, of which more shortly. But one of the really interesting things is what's happening to the world's valley glaciers. As I said earlier, they've retreated in general by 20 to 70 metres since the end of the Little Ice Age, just over 100 years ago. The European Alps have already lost 50% of their glacier volume since the Little Ice Age, since 100 years ago. And we're beginning to see now catastrophic retreat of glaciers, particularly tidewater glaciers, that is, glaciers that come down into the ocean, in Greenland and in Alaska. And you'll see there the figure for the retreat of the Columbia Glacier in Alaska. It's retreated 13 kilometers between 1982 and 2000. Glaciers don't behave like that normally. It's a staggering rate of change. Glaciers are normally like students in the morning, very slow. Like me in the morning. And also very striking is the way in which the glaciers of the tropical mountains have retreated in the last 100 years. The East African glaciers on Kilimanjaro, Kenya, occupy 1/3 to 1/6 of their former area. And the work that is being done in Latin America, I'm afraid, shows a similar picture for many of the mountainous areas of this continent. And pictures like this comparing glaciers at different times are becoming all too familiar. And all these changes in the cryosphere will have impacts on sea level. Sea level is rising. The speed with which it is rising is increasing. And during the 21st century, the rate is going to go up still further. And 5 millimetres per year equals about 0.5 metre, if my maths is right. Now, 0.5 metre doesn't sound very much, does it? So perhaps we can all relax and sleep in our beds happily. 5 metres is likely, according to the Intergovernmental Panel. That's, of course, if West Antarctica does not suddenly become destabilised, and that also depends to a certain extent on how much the Greenland ice cap will decay. And there are people who are very worried that the Greenland ice cap is very unstable, and once temperatures rise by more than about 3 degrees, it will really start to melt catastrophically. So that sea level rise rates may become even greater than 0.5. But even if they're 0.5 in this century, I think the results might be considerable. It won't be this bad. But of course, there are some parts of the world which are sinking. And again, I'm going back to sensitivity. Areas which are sinking and suffering from sea level rise will have a compound effect which will be far worse than the average. And of course, there are many parts of the world which we as geomorphologists know are subsiding. There are deltas and atolls which subside under their own weight. There are areas which are sinking for tectonic reasons. There are areas that are sinking because of isostatic compensation following changes in the Ice Age. And there are areas that are sinking because of the removal of groundwater and hydrocarbons, which I mentioned earlier, and the areas that are sinking naturally because the organic sediments that underlay them are gradually compacting. So there are many places where subsidence is occurring. Here, for example, is Galveston and Houston in Texas on the left. And being America, the contours of equal subsidence are in feet. But you can see that in the vicinity of Galveston Harbor, which is on the coast, and in the blue area, there are locations where the degree of subsidence that's already taken place is up to 1 or 2 meters. And I showed earlier that figure from Central Valley of California where there's been about 8 or 9 meters of subsidence. That luckily is not a coastal region. But cities like Tokyo in Japan and Bangkok in Thailand, as well as Houston and Galveston, Texas, they are sinking. And sea level is rising. So combine the two, obviously, and you get a much worse effect than you would from global sea level rise alone. So that's one type of sensitivity. The other type of sensitivity is that there are certain coastal environments which, because of their locations close to sea level, the role that tidal conditions play in their generation, and because of their basic fragility, may be extremely prone to change even with modest amounts of sea level rise. And I mentioned their beaches, salt marshes, mangrove swamps, which I had the pleasure of seeing on Sunday, deltas, coral reefs, and lagoons. You've only got to go down to Santos and you will see at least some of these. Here's the Mississippi Bird's Foot Delta, the most important wetland in America. Like me, it looks extremely old. It's knackered. Sorry, the translator won't understand what that means. It is not very well. It is more water than mud. It's subsiding under its own weight. Sea level is rising. Flow to the Bird's Foot Delta is being diverted to other mouths of the delta, as happens with deltas. And the Mississippi Delta has less sediment to nourish it today because of the construction of levées or embankments, and because upstream there are a multitude of dams which are stopping sediment coming down the Mississippi and the Missouri to generate the delta. So the Mississippi Bird's Foot Delta is finished. And we saw some impact of that, of course, at the time of Katrina. The Nile Delta, an area of ongoing subsidence. Sea level rise. Starved of sediment because of the Aswan and other dams. And as sea level rises, the coastline will erode and the interface between fresh and saltwater aquifers would change, causing problems for water supply. Bangladesh, the same. It's the delta of the Ganges and the Brahmaputra. And this map shows contours above sea level. 1 meter, 2 meter, 3 meter, 5 meter. And you can see the huge amount of Bangladesh which would be flooded if sea level were to rise by 1 meter. And 50% of all Bangladesh's rice production is in that zone beneath 1 meter. And it is subsiding. Cyclones may become more prevalent, causing more inundation. And so we're talking in Bangladesh probably of a 1.5 meter sea level change by 2100, with 17 million people affected. And then we have coral reefs, the most important and diverse ecosystems on Earth, apart from the rainforest. Very beautiful. What's going to happen to them? Some corals will love warmer water. Those are the ones that live in quite cool water. But those that are living in hot water, as in the Caribbean, will suffer stress. They're also going to be attacked by more cyclones of greater intensity. Will that build up coral islands or smash them down? Will an increase in sea level be slow enough for the coral reefs to build up? Or will sea level rise too fast for the coral reefs to keep up? And a lot of that will depend upon whether they're healthy coral reefs, and a lot of that depends upon whether or not they are polluted by silt, for example. And then I suspect, very importantly for this part of Brazil, is the question of salt marshes, mangrove swamps. These are very important ecologically. They're very important in terms of coastal conservation. They're very important commercially in some cases for fisheries. How are they going to fare? Well, some salt marshes, including mangrove swamp, may do better than others. And again, one of our roles as a geomorphologist is to identify those particular areas of salt marsh that may be particularly vulnerable to sea level rise. If you have a mangrove swamp, for example, it is composed of slow-growing trees, relatively compared to other salt marsh vegetation. So it may take time to adapt. If the mangrove grows in an area with not very much sediment accretion, it may become more and more flooded, which it may or may not like. If there are coastal constructions like sea walls that prevent the mangrove migrating inland as sea level rises, or if there's roads in the way, then the mangrove swamp will be vulnerable and will disappear. So there's a great research area just below the Serra da Mar for people to work on. And then there's the question of coast erosion as sea level rises. And there is a rule that has been formulated by an engineer called the Brun rule, which suggests that as sea level changes, you will get a change in the equilibrium profile of a beach. And to cut a long story short, on a sandy coastline, for a 1 meter rise in sea level, you would on average have an increase of erosion to the extent of about 100 meters. So you think of some of your favorite seaside resorts with their promenade and all their cafes and so forth, and the beach in front. That environment will be transformed. And of course, many of the world's beaches are eroding anyway. They're eroding because of the fact they're no longer being nourished, because rivers are starved of sediment by dams. They're no longer being nourished because of so-called hard engineering defense structures. And they may be being eroded because of increasing storm activity. So coastal erosion in a warmer world is likely to accelerate. So one point I've been making is that although global warming is bad enough, it's this combination of one human activity with another that really may create some of the problems. If you're a coral reef and you're affected by siltation and you can't grow very fast, you are not going to find it easy to adapt to a change in sea level. If you are the Aral Sea and all your drainage is being taken away for irrigation and the climate gets drier, you will be in a very bad way. So many hazards, in a sense going back to my first talk, many hazards will become accelerated in a warmer world. So one of the big issues for geomorphology in the future is to get involved with the campaign to make people aware of the dangerous future we face because of global warming. There are many things that we can do to take part in this debate about what is one of the most vital issues for humankind. So on that cheering note, I will stop. Thank you very much.